Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. This is Sami Al-Alwani. Hello everyone. I'm gonna talk about power electronics in power system, and I will post a lecture series regarding this course. The main reference that I will take for this course is Power Electronics, written by Daniel Hart. This book is very good as an introduction for those who don't have a background in power electronics. And the topics that I will cover for this course are shown here. I will talk about power electronics briefly as an introduction for those who don't have a background. Then I will present like few lectures about power computation, like the concept of instantaneous power, and then we will go through the first converter, which is called rectifiers, which convert AC sources into DC sources. And then I will briefly talk about AC voltage controller. Then I will go in depth for the DC to DC converters, which is called choppers. And then I will talk about DC power supplies. Then the third categories of power converter, which is inverter that convert DC to AC. Then I will talk about resonant converters. And finally, we will go into the design of drive circuits, snubber circuits, and heat sinks for the converters that we will cover in this course. So stay tuned to study one of the most important topics in power system. This is the first lecture in power electronic course, and in this lecture I will give a brief introduction for those who don't have a background in power electronics, and actually why we use power electronics in an electrical system. Whenever we have a source of power, and then we have the load, sometimes there is no match between the source and the load in terms of voltage level, or in terms of frequency, or in terms of the nature of the source. For example, you have an AC source power and the load is, for example, a DC motor, or the vice versa. Sometimes you have a load that need to be controlled. For example, if you have an AC source that is connected to an electric motor, and the motor you need to control its speed, torque. You need to play with the voltage and frequency, and the only device that can be used to change the nature of the source, or change the frequency, or change the voltage level, is called power electronics. Because the traditional method used in the past was using DC resistance, and DC resistance, as we know, dissipate too much amount of power as heat, and it's not an efficient way to be used. And I will give an example. Let's say I have a DC battery of 10 volt and a load resistance of 5 ohm, and I need a voltage across the resistance of 5 volt. What I will do, I will connect another resistance in series equal to 5 ohms to have 5 voltage drop across its terminal, and the other 5 volt will appear on the load resistance. If we measure the amount of power dissipated on this resistance, it will be like 50% of the power dissipated as heat in this resistance. So we have an efficiency of 50%, which is very low. Let us take the same circuit and replace this resistance with a switch. We have the same load resistance, the same voltage source, and we want to apply 5 volt across the load resistance. What we will do is use this switch like 50% of the cycle is on and 50% of the cycle is off, and this is called the period of the switching pattern. So if we want to measure the voltage across the resistance, it will be like during the switch is on, 10 volt will appear across the resistance, and when the switch opens, it's like 0 volt across the resistance. So if we took the average value of the voltage across the resistance, it will be 5 volt. And if this switch is ideal, meaning that there is no power dissipated during the switching pattern, then the efficiency will be 100%. So this can only be achieved using power electronic devices. And what are the power electronic devices? It's power diode as an example. There is also transistor, bipolar junction transistor. This is NPN, and also we have IGBT, which is insulated gate bipolar junction transistor. This is the emitter, this is the collector, and this is the gate. This is the base, this is the collector, and this is the emitter. Also we have power Mosfets. And each one of these, also I will present some lecture about the CR, which is silicon controlled rectifiers. This is the gate, this is the cathode, this is the anode, this is the cathode, this is the anode, And these are the most common type of power switching devices used in power electronics. And each of them has its own characteristics, and we will know about them when we use each one of these devices. Okay, now we will talk about the power computations. The first concept that we will talk about is called instantaneous power. Instantaneous power is when we have, this is a load, it has a voltage across its terminal and a current flowing through it. The instantaneous power is a time varying quantity. So the instantaneous power is the power that changes as a function of time. It will be the voltage as a function of time multiplied by the current as a function of time. Using the passive sign convention, if the power is greater than 0, then the power being absorbed. If the power as a function of time is less than 0, then the power is supplied or delivered. That means when the power is positive, this is a load. When the power is negative, this is a source. I will give an example to illustrate this concept. Let us say that I have this current waveform. This is 1, this is 2, this is 3, and this is 4. So obviously the period is 2. This is the maximum amount of current, and this is the current as a function of time. And we have a voltage across this particular device going like so. Then it's 0. Then it's positive again here. This is the voltage as a function of time. If I want to calculate the power that is being observed or delivered by this particular device, it will be the voltage times the current at each time period. So from 0 to 1, I will multiply, let's say this is 1, this is 0, let us say this is 2, this is minus 2, and this is 1. So from 0 to 1, this is at 0, it's like 0 multiplied by 2, it's 0. Then 1 multiplied by 2, it's 2. So it's 2 here. Then here it's minus 2. So it will be 1 multiplied by minus 2. It gives us minus 2 here. Then there will be a negative slope as this tends to decrease from 1 up to 0 at time t equal to 2. So at t equal to 2, this will decrease from -2 up to 0. Then at 3, it will be the current multiplied by the voltage. So wherever the amount of current here multiplied by 0, it's 0. Then 1 multiplied by the decreasing amount of current from 1 up to 0. So we will have, like, at 3, it's 1 multiplied by 1, it's 1. And then it will decrease until time equal to 4 to 0. So this is the power as a function of time. So the power being observed from 0 to 1, then the power is delivered from 1 to 2, then the power is 0 from 2 to 3, then the power is positive from 3 to 4. This is an example to how to calculate the instantaneous power from graphs shown in this example. So then to find the energy from instantaneous power is just finding the integral of this instantaneous power. So energy will equal to the power from the integral from t1 up to t2, p as a function of time, dt. So if we substitute the voltage and current, it will be the integral from t1 to t2, v as a function of time multiplied I as a function of time, dt. So, like for this example, shown here, if we have been asked to find the energy being consumed from time t equal to 0 up to t equal to 4, we have to do the integral from t equal to 0 up to t equal to 1, then add the energy from t equal to 1 up to t equal to 2, and so on, until we find the total amount of power being observed or supplied during this whole amount of time. The other concepts regarding power calculation is the average power. The average power is the power observed by a component in the time interval from t1 to t2. So if we want to find the average power, we have to define the time at which the power will be calculated. So power will be equal to, the average power will be equal to 1 over the period, which is t2 minus t1, integral from t1 up to t2 pt dt. Or we can say 1 over t2 minus t1 integral from t1 to t2 v as a function of time, I as a function of time, dt. So this is how to calculate the average power. So to calculate the average power for this particular example, we will say average power from t2 equal to 1 minus 0 integral from 0 to 1 pt dt. And from this example, this is the first power to be integrated over this time period. So it will be 1 over 1 integral of pt here equal to. Likewise, we will find the average power from t equal to 2 up to t equal to 3, and this tends to be equal to 0 watts since the power is 0 at this period. And then we will find P4 as well, average power from t equal to 3 up to 4. Finally, we add all these average powers together, and then we will get the total average power observed or delivered by this particular component here. Now we will find the average power in periodic signals. So if the current and the voltage signals of a circuit element are both periodic, means that V of t is periodic and I of t is also periodic, then and also have the same period, then the average power observed by the element over one period is defined by this equation: 1 over t integral from t naught up to t naught plus the period t multiplied by vt it dt. So it could be any time instant. We just need to study the circuit element for a time interval of length t. So in inductors, for example, with periodic currents, let's say this is the inductor. The current that is going through this inductor is periodic, and the voltage across the inductor as a function of time is VLT. Then VL is equal to L di as a function of time dt. So if IL is periodic, that means that IL will be t plus the period t will equal to the current at any time I of t. Then the average power This is the symbol for average. The average power across the inductor, the average power across this inductor will equal to 0. That means there is no current, there is no power being observed or delivered by the inductor over that period. It means that the average power across the inductor is 0. This is only if the current is periodic. Also, the average voltage across the inductor is equal to 0. Then the capacitor with periodic voltage, if we have this cap and the voltage VC across the cap is periodic, and then there is a current going through the cap, IC is equal to C dVC over dt. If VC is periodic, then the average power across the cap is also 0. And the average current moving through the cap is also 0. Example number 1, we have a periodic voltage and current with a period equal to 100 microsecond. The voltage is 50t when t is greater than 0 and less than 70 milliseconds, and 0 between 70 milliseconds and 100 milliseconds. Then the current is 0 between 0 and 50 milliseconds and 4 amperes between 50 milliseconds and 100 milliseconds. So if we look at these two waveforms, and they asked us in part A to find the instantaneous power P as a function of time. As we know that the voltage as a function, the power as a function of time is equal to the voltage as a function of time multiplied by the current as a function of time. So there are two ways to solve this numerically, or you can draw the voltage and current waveforms and then multiply them according to the graph. So if I want to plot the voltage waveform as a function of time, this is the period, which is 100 millisecond, and this is 70 milliseconds. The voltage is said to be 50t when t is greater than 0 and less than 70 milliseconds. So at 0, the voltage is 0. At 70, we multiplied 50 by t, which is 70 milliseconds, which is 10 to the power minus 3. And this will gives me, if I use the calculator, this will gives me 3.5 volt. So at 70, let's say this is 3.5 volt. Then it's 0 otherwise, which is between 70 and 100, as it mentioned in the voltage function. Then the current as a function of time will be This is 50 milliseconds, and this is 100 milliseconds. It will give me 0, between 0 and 50, and then 4 between 50 and 100, so 4 amps. If I want to find the power is simply the multiplication between the instantaneous voltage multiplied by the instantaneous current. So between 0 and 50, the multiplication between voltage and current will give me 0. And then between 50 and 70 millisecond, the voltage at 50 millisecond will be 50 multiplied by 50. This will give me 2.5 volt. So 2.5 multiplied by 4, this will give me 10. Say this is 10, and then up to 70, it will be 4 multiplied by 3.5, so it's 14. So here it's 14 watts and here is 10 watts, and then from 70 to 100, since the voltage is 0, it will be 0. So the power will only be 0 when time is greater than 0 and less than 50 milliseconds, and then 10 watts when time is greater than 50 milliseconds and less than 70. It will be 10, not 10, it will be it will be 50 multiplied by 4, which is 200 T, when T is greater than 50 milliseconds and less than 70 milliseconds. So if we add, instead of T 50, it will give us 10 watts, and 70 will give us 14 watts. And then 0 when T is greater than 70 milliseconds and less than 100 milliseconds. So this is the instantaneous power. For the average power, to find the average power of this component, we will only evaluate the power. This graph, we will evaluate this power for 100 millisecond period. So the period is 1 over 100 multiplied 10 to the power minus 3, and the power is positive only at this interval. So it will be from 50 milliseconds, which is 0.05, up to 70 milliseconds, 0.07, 200 t dt. So it will be 1 over 100 multiplied by 10 to the power minus 3, 200 multiplied by t square over 2. Evaluate this between 0.05 up to 0.07. So the answer will be 10 multiplied by 200 over 2 is 100, multiplied by 0.07 squared minus 0.05 squared. So the answer will be 1000 multiplied by 0.0024, and the answer is 2.4 watts. This is the average power. Then to find the energy over the whole interval, integral from 0 to t pt dt, from 0 to 50.05 seconds 0 dt, plus from 0.05 up to 0.07 200 t dt, plus from 0.07 up to 0.10 dt. So energy will equal to from 0.05 up to 0.07 200 t dt, and this will be equal to 100 t square from 0.05 up to 0.07. So the energy will equal to 0.24 watt second or joule.